Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar. How to increase performance and reduce cost with optimized system memory in FPGA designs. Brought to you by Tech Online, MoSys, Arrow, and broadcast by AspenCore. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the green folder icon located at the bottom of your screen. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window and then click the Submit button. Please note that we'll try to get to as many questions as we can in the time that we have left at the end of today's program. However, if we're unable to get to your individual question today, someone will get back to you after the program is over. Also at this time, we recommend that you disable your computer's pop-up blockers, and at the end of the webinar, we will ask you to complete our feedback form. Your feedback will provide us with valuable information on how we can improve future events. You can also launch the survey at any time by clicking on the red survey button at the bottom of your console. And if you're experiencing any technical problems, please type your issue into the Q&A text area, and we will be glad to offer one-on-one assistance. And now on to the presentation, how to increase performance and reduce cost with optimized system memory in FPGA designs. Discussing today's topic are Gus Lignos, VP of IC and IP Sales, MoSys. Gus has 30-plus years of experience in semiconductor sales, and prior to joining MoSys in 2010, Gus held senior sales positions at Texas Instruments, IDT, NEC Electronics, Tensilica, and NVIDIA. And joining him today is Mark Baumann, Director of Product Definition and Applications at MoSys. Mark brings more than 20 years of engineering management experience in the semiconductor industry, and his specialties include product definition, PCB and silicon design, building and leading teams, and program management. And finally, our final speaker today, Scott Irwin. Scott has over 30 years experience, Scott Irwin, VP of Line Products at MoSys. Scott has over 30 years of experience in the semiconductor industry, joining MoSys in 2010 via its acquisition of MagnaLinks, and prior to founding MagnaLinks, he held executive management and design roles at Xilinx, Rocket Chips, and Rockwell Collins. It's with great pleasure I now turn this special session over to Gus to begin. Gus, take it away.
Thanks, Chris. I want to point out that we will make the slides available to you right after the presentation. So Mark Baumann will cover the product details, but I wanted to give a background on MoSys, the company. So who is MoSys? MoSys is kind of like that company with cool advanced technology that you may not have heard about. And that's why we are partnering with Arrow. We want to make sure that we can use Arrow's touch to so many companies that may not be aware of the products and technology that we have. So today's goal is to show how using MoSys products can save cost, reduce your design time, increase features, and increase performance in your systems. So brief history about MoSys. We were a spin-out from IDT back in the early 90s. IDT did multiple spin-outs back then, QED, which was 64-bit MIPS processors, Galileo that did switch chips. Both those companies very successful and were acquired by larger companies. And MoSys, which was an IP company originally. MoSys invented the 1T SRAM cell, which was a memory cell that was innovative at the time and still is. Very compact cell size, increased speed, and better soft error rate performance than traditional 6T SRAM cells. So that 1T SRAM cell was the building block of TSMC's embedded DRAM process. And the company was cruising along, selling the IP, doing very well. But then the decision was made about 12 years ago to use that IP and transition to become a fabless IC company. So former IDT CEO was brought on board to be the CEO of MoSys, a guy by the name of Len Parham, well known in Silicon Valley. He was also at the time the chairman of NetLogic. And then he brought in the former CTO at IDT for many years, Michael Miller, who is the MoSys CTO now, and Mark Baumann, who you'll hear from in a minute, who is now our Director of Applications and Product Definition. And Michael Miller and Mark Baumann, they built the TCAM business at IDT. It was a very successful business. back in the day at IDT. And the point of all that is there's a lot of networking and memory architecture expertise in the company. So with that, MoSys bought two SerDes companies, and that's where Scott Irwin came in. We bought one for high performance and one for low power. And we mated the SerDes technology with the very high performance memory and created a family of products called the Bandwidth Engine family. So these products have a serial protocol, very efficient chip-to-chip protocol. Mark will get into that. And it's a high access rate memory with intelligence on chip. And we're on our third generation of Bandwidth Engine products. Mark will go through all those details with you. And the point of all this, again, is by using smart memory architecture design and MoSys products, you can dramatically reduce your system costs, reduce your design time, add features you might not be able to add with traditional memories, and improve your system performance. I'd like to share a story. I was at one of the networking shows a few years ago. I think it was Interop or OFC, and I was sitting with the FPGA architecture team, and Mark was with me at the time. We've been working with this company. They're a multi-billion-dollar company, and they wanted to use the Bandwidth Engine products, our serial attached memories, and replace what they were using before, which was QDR memory. So they had to convince the VP of engineering to make the change. And we're sitting at the table at the conference, and the FPGA architect is telling the VP of engineering in front of us, hey, if we use the MoSys Bandwidth Engine and replace the QDR, we can reduce the design time on the FPGA cards by 6 to 8 weeks and add some features we couldn't normally do. So they're telling that in front of us. It was great. And it turns out they ended up designing us in, and now we're used across all of their new platforms in a wide array of different types of applications. So it's very, very gratifying. And that's the kind of thing we hope to share with you to give you some ideas of how you might do things a little differently and get the benefits I talked about. Again, add features and increase your performance, lower costs, and reduce your design cycle times. Next slide, please. Or maybe I do that. Okay. So these are the products that we'll talk about. There's the QUAZAR family, which is the lowest cost QDR replacement device. There's the BLAZAR family, which is also a QDR replacement, but it adds some on-chip intelligence, namely some on-chip ALUs for read, modify, write functionality and burst capability. And we also have the PHE, which stands for the Programmable HyperSpeed Engine, which has embedded 32 RISC cores. There's 32 of them. They're 8-way threaded for algorithmic acceleration. So these are great for TCAM alternatives with much higher capacity than TCAMs. And again, you might have heard of Tom Reardon, who was one of the early founders of MIPS, and he was the founder of QED. So Tom helped architect that along with Michael Miller and Mark Baumann. And it's a great alternative to TCAMs. We'll get into that. All three of those products, QUAZAR, BLAZAR, and the PHE, offer you 4 to 8 times the capacity of a QDR SRAM. And you can reduce your system costs on a per bit basis. It's a big win, both as far as system layout and system cost. We also have a family of IP, which we call Stellar, which is the packet classification IP, which can do hundreds of millions of searches per second and millions of lookups. And the last product line, which Scott will talk about, is the Linespeed products. These are 100 gig PHY ICs. They're common functions that you know about, gearboxes and retimers, but we also have our unique features above what you might find from the big boys in the market, Broadcom, Marvell, and Inphi. They're every bit as good as those guys, with some added features. And by the way, because we're MoSys and not those guys, we will support even through distribution, and with the distribution customers, you'll get direct access to our apps team, and we'll be very aggressive on pricing. And with that, I want to say thanks for joining us, and I'll turn it over to Mark.
Okay, this is Mark Baumann. I want to also thank you for taking the time out of your day to help to join us and let us explain some of the MoSys devices that are on the market today. What I'm going to start out with here is kind of a roadmap slide that talks about how these products are divided into both a I/O speed and a density. So if you look at the horizontal axis, you'll see the 12.5 gig and the 576 meg. And the box that is drawn above that, those are the products that fit into that category. And further down the line here, you'll see that there are products that have SerDes rates of up to 25 gig and are as dense as 1 gigabit in density. So we've separated them out that way, and we'll talk about the vertical axis, which is the functionality differentials that you'll see across the lines. All these products are the ones that we're going to talk about today. And again, what we're going to do is try and relate how the bandwidth performance is associated with the architecture that we defined in the part itself. So if we look at this, we're going to spend quite a bit of time on this first slide here, and we want to go through the architecture of the device, and we'll relate that in future slides as to how that benefits system performance. But if you look at the top of the slide, the 10 to 25 gig, you see the RX SerDes lines. So MoSys has defined these parts and used a SerDes interface as opposed to a wide parallel bus. We wanted to do that for a few reasons. It does ease design of the PCB because SerDes are relatively easy to lay out, even at high frequency at 25 gig. They're not that difficult to lay out anymore. It's very common to do. And we wanted to save interface on your host processor as well, whether it's an FPGA or some other ASIC that you're going to use. The 25 gig seems to be a very common structure that you use today. The other thing I want to point out is that you can see they're separated into two groupings, and we call them GCI-A and GCI-B. As Gus mentioned, we have this interface protocol that we defined as gigachip interface. So we've used this interface because it's designed specifically to interface with memories. They're low latency, high efficiency protocol that you could use on a SerDes lane. And so again, they're divided into these two blocks of 8 SerDes each. So a total of 16 SerDes, allowing for the RX and TX both down the bottom. So then after we get through the GCI protocol and it comes in, you have a request comes in on one of the GCI ports. It's then handed off to that block that's called memory controller. The memory controller really is steering logic. What will happen is you'll have a request come in. It will steer to the appropriate memory structures that are in the center of this diagram. So again, now if we look at the center, you see there's 4 vertical structures, and there's one box drawn around the first one, and we call those partitions. So we've broken this device down into 4 partitions, and within the partition, that is broken down into a subdivision which we call banks. So you can see there's lots of levels of structures built within the memory itself. So we have in the smaller device, the 576 megabit device, there are 64 banks per partition. In the larger devices, the 1 gigabit devices, there's twice that. There's 128 banks of memory within each partition. Again, we'll relate as to why we did things like that in future slides, but that does add to the architectural benefits of access and throughput of the device. And the other thing I wanted to point out is you can see at the top of each of the partitions, there's 2 little arrows in, and at the bottom, there's 2 little arrows out. What we're trying to point out there is that what also is built into this device is the ability to do multiple operations concurrently. So this is pointing out for the smaller device, we can do 2 writes, and the bottom shows 2 reads occurring simultaneously within each partition. So that means in the smaller device, we can do in 1 memory cycle, 1 TRC, we can do 8 writes and 8 reads because of the structure of this device. Again, allowing for very high bandwidth. And at the bottom, the results mux there essentially is just logic that would then steer whatever request came in on GCIA goes back out on GCIA. Whatever came in on GCIB goes back out on GCIB. So again, we just wanted to show that internal architecture, and that's going to relate to some of the other future slides that we'll talk about. And again, you can see that each of these has up to 8 SerDes lanes per. Okay, so we're going to move on, and again, if we look a little more detail into one of the partitions, I talked about the banking structures within those partitions. These colored arrows that you can see really relate to, up at the top would say 2 write structures are happening, and the bottom are 2 read structures happening. Okay, and the only limitation that you have is that any write or read has to occur into an individual bank. The banks are single ported structures. So you can do 1 write or 1 read out of each bank. But you can do them concurrently. So if you wanted to do 2, and in the larger devices 4, you can. So again, that on the larger devices, that means with the 4 partitions, you can do up to 16 writes and 16 reads simultaneously in 1 TRC or 1 memory cycle. Again, what that leads to is, as the top points out, the header here, that you can get up to 1.7 terabits of bandwidth within the device itself. Again, we'll go through why this benefits things later on. The other thing I wanted to point out here is to show you how we relate to other devices in the market, right? So if you look at the QDR Sigma quads, there's these charts that show you the kind of performance that you can achieve out of utilization of these devices. And you can also see that what the bottom horizontal axis is showing is a percentage read versus percentage write. So you can see all the standard memory products. They're really designed for accessing parallel common writes and reads, right? 50% reads, 50% writes. That's really what they're designed to do. What the MoSys product, on the other hand, we've designed it a little bit differently, where we're looking at 75% reads and 25% writes. So memory access is where you don't constantly just go back and forth with writes and reads. So table kind of structures. But you can also see that even with that structure, the internal architecture of the device, we can outperform the standard QDRs and Sigma quads in the market today. So again, I wanted to point that out and relate that to what does that mean as far as just physical numbers. Well, if you look at the numbers, and let's take the bandwidth engine device using 16 lanes at a burst length of 8 is that top right block, right? It says 320. So that means that with that kind of architecture using our 25 gig SerDes, you can get 320 gigabits of data in and 320 gigabits of data out. So these are significant numbers, and you can achieve this with SerDes, even though a lot of people don't equate SerDes to memory products. The other thing I wanted to point out is down the bottom there, you can see the green, red, and purplish or bluish lines. Those are the performance numbers you achieve with the other memory products that are on the market today. So again, you can see how our performance and throughput is much higher than the other products that are out there. I wanted to just briefly talk about the applications and why we designed it the way we did. The bottom left hand where you can see the single chip buffer description on the top of the block. This is where you might do the 50% read, 50% write application, right? So there's what we called oversubscription buffers, whereas, when you have a system and there's this burstiness of traffic, you have high traffic times and low traffic times. where you don't want to necessarily design your system for the worst case, handle the worst case all the time. You might over-design it and just be cost ineffective. So quite frequently you'll do something like put a buffer in that says I can absorb this high traffic time, let my packet processor or host actually catch up, and then feed it at the line rate that it can absorb it. So that's a very common application, and that's where the 50% read, 50% write would come in. If you look at the bottom right-hand corner, the high access rate tables, that is the one where you might more commonly use the 75% read and 25% write. That's an application where, again, you don't update these tables all that often, but you read them quite frequently. And then the top right-hand portion of this is showing some of the things that Gus talked about with the in-memory functions that we offer between the burst and the ALUs and read, modify, write structures. So that's where that's coming in, and those help us add some functionality without adding a lot of complexity to the device itself. And the last one that we talked about is, hold on here, let me see, are we, am I not being heard? Hold on.
I hear you just fine, Mark. Go ahead.
Okay. I apologize. I was distracted a bit here. The other thing is we talked about the 4 partitions, and each of those partitions was 2 meg by 72 in density. So when you equate that to a QDR device, that's 1 QDR device. So you can see kind of straightforwardly the 4 partitions that we have within one device can equate to the same densities and throughput that we get with 4 QDR devices. And we also started looking at the routing on a PCB. So if you take 4 QDR devices, there's literally hundreds of pins you have to route, and they have very strict layout requirements. Whereas in the bandwidth engine devices, because we use SerDes, you have that flexibility that SerDes have of a little longer routes and not quite so intolerant of matching things. So the basis of hundreds of pins versus 32 pins is really beneficial to a lot of PCBs. And that even doubles, gets worse. You can get up into the 1,000 pin area if you were trying to put down 8 QDR devices versus 1 bandwidth engine, which is, again, down to the 32 pins. I think this is the time when we have our first polling question. I'm going to hand it back to Chris to talk that through.
All right, thank you, Mark. This is our first of several polling questions. I believe there are 4 in today's program. And to participate in our poll, all you need to do is click on the radio button next to the answer that is appropriate for you, and then click the submit button. We'll take a look at the results after everyone's had a chance to go ahead and input their selection. Our question for you here, our first one, do you have high bandwidth FPGA applications, 80 gigabytes per second or above aggregate line rates? And your answers here can be design 80 gigabytes per second or above aggregate line rate boards for either test and measurement, networking, and security. The second one is I'm considering using TCAMs. The third answer that you could have is my application includes packet header inspection, payload inspection, and lookup tables. And our final answer that you could choose is my application may need small 5 to 10 milliseconds ingress or egress smoothing buffers. So go ahead and click on the radio button next to the answer that's appropriate for you. We'll take a look at those results momentarily, and also right now is an ideal time to ask a question. If you'd like to ask a question, you can simply click on the Q&A icon, type your question in, and then click the submit button. We'll give you a few more moments here for everyone to go ahead and submit an answer. We encourage your participation. and then we will take a look at the results here momentarily. Okay, so let's go ahead and take a look at our results. It looks like we had about 25% say design 80 gigabytes per second or above. Using TCAMs was about 33%. My application includes packet header inspection was about 33%. And I may need small 5 to 10 millisecond ingress or egress was about 8%. So Mark, your thoughts on our first polling question.
Yeah, no, I appreciate the feedback, and it actually looks like it's what drove us to design the part the way we did. And again, because there's all these different possible applications that you could use. The TCAM thing we'll talk about in a little bit. That's that's interesting that about a third of you are interested in TCAM functionality. And again, that smoothing buffers and header inspections are, again, really interesting that more than half are interested in that. And those are the functionalities that we'll be talking about shortly here. So that's really interesting. Appreciate your feedback. Okay, I'm gonna take over then and pick up with some of the other functionality that we've built into this device. And you can see how it might equate to some of the feedback that you gave on the first question. So the burst and RMWs are what we had called in-memory functions that we did. And what we really wanted to do is look at what are the common functionalities that someone uses in systems, but it doesn't burden the device by putting a lot of logic into it. And burst and RMWs seem to fit nicely into that. So if you think about all a burst does is you say, hey, I want the next 8 words, and the next 8 words are going to come back, as opposed to having to say, give me 1 word at a time 8 times. So we've built that very simple logic into the device. And what it does is lets you, as the customer, just issue 1 command and then receive 8 results, up to 8 results back. You can do 2, 4, or 8 results back. And again, what that does is frees up your host to have some free time to go do some other structures or some other functions. So it's a relatively simple thing to do, but it does have some real benefits as far as bandwidth and throughput. And then the second one is even more kind of release for the host or processor. So it's an offload where you can do something similar to an RMW where you would normally have to do a read, wait for the structure to come back, modify it, and then write it back, right? So there's a couple of bus transactions that would have to occur and some processing time that the host would then have to take up as well. Well, those are relatively simple operations, and because we built in the ALUs that were mentioned earlier, they are the function that could do the read, modify, write internally. And again, what we've done is made sure that the data structures are valid before we modify them. We actually even built ECC into this device to make sure that we don't modify a corrupted piece of data. So there's it's relatively simple to do, but it really does benefit and saves a lot of time on the host side to do that. And it opens up the options, as was pointed out earlier, to add functions that you may not normally want to do, right? So if you wanted to do something like keep statistics on maybe byte and packet counts of what's coming through your system, that's a lot of overhead for the host to take care of, whereas it's all self-contained in the bandwidth engine devices themselves. The other thing I wanted to point out here briefly is we talked about, the GCIA and GCIB ports. Well, the benefit of doing that is that you now have separate ports, and they potentially can run at even different speeds. So what that allows you to do is act like a true dual-ported structure. So if you had, multiple hosts And what you're doing is passing data. One host does one function, one calculation, and hands it off to the next. Even like, image manipulations and convolutions. That could be very straightforward with a device that acts as a dual port. And in these devices, you actually, because the devices are separated port-wise, you can actually have one port talking to one host, a separate port talking to a different host, and it even allows that to happen at different frequencies. So if one of your hosts has to run at a much higher frequency because it's doing other calculations, then it allows that kind of a clock data crossing to occur within the device itself. And I think we're into our next, I'm going to hand it back to Chris for our next polling question.
All right, thank you, Mark. We are on to our second polling question again. If you'd like to respond to our poll, just click on the radio button next to the answer that's appropriate for you. If you'd like to ask a question, you can do so by clicking on the Q&A icon and typing in your question, then clicking the submit button. And we'll get to as many of those during our Q&A coming up here as we can. If we don't get to your question today, someone will get back to you after the program is over. So our second question for you, do you have a design that uses QDR or sync SRAM or sync SRAM that would benefit by having by having more high-speed memory than the QDR provides? And your answers here can be, I use one QDR and would benefit by having 2 to 4 times the density. I use QDR for the access speed, but the density is limiting. I use multiple QDR devices, but the routing is impacting my PCB design. Or your final answer, QDR answers all my needs at this time. So we'll give you a few moments to go ahead and input your answers, and then we'll take a look at those results. Again, this is the second of 4 polling questions that we have for you. And if you'd like to ask a question, you can do so at any time just by clicking on that Q&A icon. So let's take a look now at our results. And it looks like 20% said I use one QDR and would benefit by having 2 to 4 times the density. I use one QDR for access speed was 20%. And 10% said I use multiple QDR devices. And 50% said QDR answers all my needs. So Mark, your thoughts on our second polling question?
Yeah, this is also very interesting. I'm appreciative of that. I'm surprised actually at the last answer. The QDR answers all my needs at this time. It's interesting to me when in a lot of the conversations we've had with customers, when we talk to them, it's very unusual to find where people can say, the memory I have is all I need. Usually, certainly if you're a software guy, usually there's never enough memory for what you want to try and do. But it's fascinating to see that QDR answers all the questions. We have quite often found that since there's no roadmap for QDR, that they're always looking for what is my next thing, and as systems get faster, you're always looking for a little bit more data. But this is, again, very interesting. I appreciate the feedback. What I'm going to do is, because we're running, want to keep moving here, I'm going to move on to a brief discussion about the QUAZAR family. Again, what we're doing is, the QUAZAR is our low-end, low-cost family, and it was designed specifically to address any of the QDR kind of operations that might be out there. And again, what we saw is it's a basic SRAM kind of application where you do reads and writes and no additional operations other than reads and writes, so no bursts, no RMWs. So we wanted to address that with a lower cost, higher density option to open up, again, the ability to go to maybe a higher throughput or higher buffering capability supported by one device. And again, what we've offered here is as you can see in the crude block diagrams that are on the left there, that either 2 meg by 72 per partition or 4 meg by 72 allows you to replace either 4 QDRs with one device or 8. So it's fascinating to see how you can replace this many with just 32 pins, and again, give you much more density and throughput. So it really was to address that next generation market that QDR seems to be leaving behind. The BLAZAR family, again, what I wanted to point out with this is that the QUAZAR and BLAZAR families are actually pin compatible with one another. So it would be possible to even start with something like a QUAZAR, just a straightforward memory, and then add functionality later. Or you could just start with the BLAZAR and even back off to the QUAZAR. But these are the devices that have the in-memory functions, the burst and the ALU functionality built into them. Again, it has the same density and all that, so you can equate that if you put it in to replace 4 devices, you could still replace 4 devices and just add features and functionality to your system. Again, so these are the devices that are pin compatible and allow you to then do burst, so the multi-word accesses and the RMWs, or keep track of statistics and maybe do metering as well. The other thing I want to make sure you understood is that we have talked about it being FPGA compatible. And the reason for that is that to implement the GCI protocol, you need to do some logic within the devices. We have, in past, we have absolutely ported to both Intel and Xilinx, but we've had no problem with either one. If you have any device that has a CEI compatible SerDes, we've had no problem with interfacing with those as well. So, but we do have RTL that's also available for each of the Intel and Xilinx FPGAs that implement our protocol. And the last thing I wanted to point out real quickly is that all these devices that we're talking about have been qualified. They've gone through full HTOL qualification, full package and latch-up kind of qualifications, and MoSys is an ISO 9000 certified supplier. So these are all supplied in carrier and enterprise grade markets that we, most of our customers have high quality requirements for these devices. Again, we've shipped hundreds of thousands of these devices and essentially no returns on these at all. The next and the highest end one that we want to talk about real briefly is the programmable HyperSpeed engine. This is, as you can see from the block diagram of this, it's very similar in architecture to the bandwidth engine products that we've been talking about. Again, we have at the top and the bottom, they're the SerDes, or the structures that use input and output. We use that same GCI protocol. The difference being that we built a little scheduler in the middle, that block that hands off to the memory products, and now the scheduler has to also hand off to the processor engines, which is, as Gus mentioned earlier, there are 32 multi-threaded processors available within this device. Now, what that allows you to do is define your own in-memory function, right? If you had some algorithm or some other functionality you wanted to make, system specific for your application, that capability is now built into a device, a literal single device that you can plug anywhere in your system, and it will let you do that. Now, the other thing I wanted to briefly point out is, that massive bandwidth that we provide for the part internally, that 1.7 terabits of data movement, is partly because we knew we eventually wanted to do something like this. And that allows both the requests to keep coming in through the GCI port, so if you have access to memory that you want. But it also allows the processing engines, which do have their own iMemory, instruction memory, and localized SRAM, but they also have access to the entire 1 gigabit of memory that's available in here. So we wanted to make sure that the bandwidth in and out wouldn't interrupt the requests that are coming in over the GCI ports. So this is all, you know, kind of the next gen thing, so you can define your own in-memory function and extra functionality that you might want in your system. Again, briefly, I'm going to show the instruction set. It's a rather robust instruction set. It has, you know, all the bit manipulation things, some specialty functions like hash, lots of test and branch and load and store instructions as well. So this is rather robust, and as Gus mentioned earlier, it's, you know, the history of this comes with MIPS background. So these guys are all the designers of this processors were all MIPS his history in the background. So. And then finally, I wanted to just show a summary of what we've been talking about here. And if you look at kind of the center of this table, there's a bandwidth max line in there, column actually in the device. And you can kind of see that the offerings from MoSys are from the MSP220. You can see that they're around 120 gigabit per second devices, up to the programmable HyperSpeed engine, which is up to 717 gigabits of access. And then the bottom row is just RTL. And I haven't mentioned too much about that, but RTL is something that we at MoSys offer as support for these devices. And again, it implements the protocol and things internally to make it easier to bring your system up and running quickly. And then we're going to hand this off again back to Chris for the next question.
All right, well, thank you, Mark. This is our third of 4 polling questions here. Again, click next to the radio button that's appropriate for you. Click the submit button, and we'll take a look at the results momentarily. We'll be coming up to our Q&A also shortly. So if you'd like to ask a question, simply click on the Q&A icon, type your question in, and then click the submit button. Our question here for you, our third question, do you need packet classification IP for your FPGA? And your answers here can be, I would prefer to use FPGA RTL IP and on-chip SRAM and or external DRAM to do packet classification and search versus external TCAMs. Another answer can be, I will implement exact match, LPM and or ACLs. And our third answer, I need to use HBM already, so packet classification IP that can leverage this would be valuable. And our final answer that you can submit, I will implement security functions like firewalls and anti-DDoS. And we'll give you a few moments to go ahead and input your answers. Then we'll take a look at the results. And again, our Q&A is coming up shortly, so go ahead and start submitting some of your questions, and we'll get to as many as we can. If we're not able to get to your question today, someone will get back to you after the program is over. So let's take a look now at our results. And it looks like 25% said they would prefer to use FPGA RTL IP. No one selected exact match and LPM. We have HBM already was about 62%. And I will implement security functions like firewalls and anti-DDoS was about 12.5%. So, Mark, your thoughts on our third of the 4 polling questions.
Okay, this is, again, what we'll do is we'll talk a little bit about some of the IP that we're offering that actually takes advantage of, you know, trying to eliminate the need for an external TCAM with the search IP that we have right now. That's available. And then using HBM is fascinating as well, because I know that the devices with HBM on them are a little bit on the pricey side. But they, again, we have also found that they're becoming very common these days, and to take advantage of that allows you to have larger table sizes and even up the frequency at which you can operate. So this is very similar to the feedback that we've been getting from some of our other customers as well. So I appreciate that. I'm going to step up the frequency here a little bit because we're running a little low on time, and I know we want to get to some questions. The Stellar Packet IP classification is the packet classification software. This is an IP offering now. This is not a device that's offered from MoSys, but it is IP. We directly wanted to go after TCAMs and that kind of functionality of ACLs and LPMs. It's called a graph memory engine that we use, and this is anything that you would think of that would have to walk down through graphs to come to an answer. This is a structure that we've built, and it's available in pure C code, so you could run it on an x86, or if you want a little bit more performance, you can do it in RTL in the FPGA. So again, this is an option. We just wanted to let you know that it is available and that we have it available from MoSys right now. Again, I'm going to push through a couple of these kind of quickly because of time concerns. But again, you can see we have these two classifications of lookups that you might want to do with this longest prefix match or access control list kind of functionality is also already built into this device and available. I'm going to hand this off to Scott Irwin, our VP of Linespeed products, to talk for the next minute or two here.
All right, thank you, Mark, and good morning, everyone. I'm going to provide you a brief overview of the MoSys Linespeed product line, which is our family of physical layer transceiver or PHY devices. I'm going to go through this rather quickly at a high level, just in the interest of time. If you could focus first on the left-hand column under applications. These applications are based on a combination of industry standard functions plus additional unique features that set us apart from others. They range from the first item, which is extending the reach of high-speed serial links by recovering and regenerating the signal. We have devices that support up to 20 lanes at up to 28 gigabits per second, and each lane can be its own independent baud rate. The second application involves interfacing to 100 gig generation of optical modules, such as the pluggable QSFP28 standard. A Reed-Solomon forward error correction, or RSFEC coding, is employed by most of the 100 gig optical interfaces to meet the low bit error rate required of the various 100 gigabit Ethernet standards. We offer this RSFEC encoding and decoding embedded in the device. And we offer devices with both 4x25 gigabit retiming as well as 10x10 to 4x25 gig gearbox devices with this feature. For example, the gearbox device with RSFEC allows a lower cost FPGA with 10 gigabit IOs to interface to QSFP modules by converting to the 25 gigabit signaling with the RSFEC encoding. This can reduce the overall cost of an implementation via the low cost FPGA plus the gearbox device. Just as the gearbox device can support interfacing to lower cost FPGAs, we also have a unique multiplexing demultiplexing feature or function. This allows aggregating two lower speed links into a single higher speed link. Can be either used to increase or double the throughput for the same number of pins or reduce the number of pins by half for the same throughput. The fourth application is similar to the standard 100 gig gearbox mentioned above. However, it supports breaking out to the 4x25 gig port into 10 independent 10 gigabit Ethernet lanes or links. This is done by utilizing the multi-link gearbox standard defined by the Optical Internetworking Forum. So this can provide port expansion for dense 10 gigabit Ethernet breakouts without sacrificing aggregate throughput or increasing pin counts, etc. And the last application I want to highlight is a unique feature we have, which is brings high availability systems and serial interconnects by supporting an active standby redundant link capability. On the right side, you'll see a list of key features. In the interest of time, I'm not going to go through each of them. I just want to highlight the embedded RSpec encoding and decoding, along with our very aggressive pricing. Finally, at the bottom, there's a summary of the various devices in the Linespeed family and a matrix of the key features and functions supported by each. And with that, I'd like to thank everybody for your time and attention, and now I'll turn it back to Chris for the next polling question.
All right, thank you, Scott. Our fourth and final polling question here for you. Again, just go ahead and click on the radio button next to the answer that's appropriate for you, and then click the submit button. This one says, do you have any applications that may use 100 gig PHY retimer or gearbox devices? Your answers here can be, I may use gearbox 4x25 gig to 10x10 gig interfaces for 100 gigabyte Ethernet with FEC option. I may use multi-link gearbox 4x25 gig host to 10x10 gigabyte Ethernet SFP plus and or QSFP plus. Another one says I may use retimer 4x25 gig, 10x25 gig full duplex with 100 gigabyte FEC option. And another answer you could select says I may need serial link redundancy and or 2.1 multiplexing, demultiplexing. And our final answer that you can select, I use Broadcom, Inphi, Marvell 100 gig PHY devices and would consider an alternate source. So go ahead and click on the radio button next to the answer that's appropriate for you and queue up your questions. We're going to go to the Q&A here momentarily. We are going to stay on for a couple of extra minutes so that we can get to some of your questions. So please do stick around. And at this point also, just as a reminder, you will find that in the green folder icon at the bottom of your screen, you'll be able to go ahead and get a copy of the slides, and I'll mention that again in a moment. Let's go ahead and take a look at our results. It looks like about 12.5% said I may use gearbox for the 100 gigabyte Ethernet with FEC option. I may use multi-link. No one selected that. And I may use retimer was about 37.5%. I may need a serial link was 25%, and I use Broadcom was also 25%. So Scott, your thoughts on our final polling question before we have you wrap it up.
Yeah, it's an interesting mix of answers. It's kind of what I expected. We actually see quite a bit in our own customer interactions. The item 2 there, which I see nobody clicked, which is for dense breakout. It's actually one of the largest applications in the family. As I said in my slide, you know, we have a mix of standard features as well as some unique features, and that, you know, it looks like that's what people have selected. So it's interesting, and it's good to see that people, for example, have the need for the mux-demux function because that's a unique feature that we offer in the Linespeed product line.
Okay. I think what I'll do, this is Mark again, Mark Baumann. I'm going to just take over for the last 2 seconds here. And again, we wanted to just close it out by, again, just reiterating some of the things we talked about, like some of the common applications of buffering, load balancing, image processing that we now offer through the MoSys products. And again, show you that little summary table. But I just wanted to spend a little bit of time and get through this so that we can get to some of your questions. And we all wanted to thank you for your time and really want to open it up to the questions. But again, if we don't get to everything, please feel free to contact your Arrow support personnel. We will be in contact with them as well, and we can continue this conversation on potential use of products that MoSys can help you, maybe help your system improve performance. So I just want to thank you again for your time. We'll turn it back over to Chris, I guess, for questions.
Yes, absolutely. Thank you, Mark, Scott, and Gus, for a great presentation. We're now going to move on to the question and answer portion of our event. As a reminder, please fill out the feedback form that will open up at the end of the show. Thank you in advance for filling out the feedback form. Your participation in this survey allows us to better serve you. We'd also like to let you know that the slides are now available. Please refresh your console now by hitting F5, and you will be able to find them in the green folder icon at the bottom of your screen. And we are now going to move on to the question and answer portion of the event. As a reminder, if you'd like to ask a question, simply click on the Q&A icon, type your question in, then click the submit button. We'll get to as many questions as we can here in the time that we have left. If we don't get to your question today, someone will be getting back to you after the program is over. So gentlemen, a lot of questions coming in. Our first one says, is there a, I guess it's going to say standard FPGA IP for the SerDes interface you describe, and can you answer that one for us?
Sure, I'm Mark. I'll answer that. Yeah, the standard interfaces on pretty much all the FPGAs that are out on the market now are the Common Electrical Interface, the CEI standards. And as long as you use one of those, we're fine with hooking up to it. We've had no issue doing that.
All right, thank you, sir. We'll move on to another question here. This one says, from a speed standpoint, how do your products compare to TCAMs?
Okay, this is Mark again. I'll try and answer that one. Yeah, we've been able to achieve the same kind of throughputs that the standard TCAMs get. So if you're talking about 300-400 mega searches per second, those are achievable with the GME product, the IP product that we offer. One of the real benefits of having a product like the Stellar product, the IP product, is that it is an RTL structure, either RTL or code. And because it is that, you can have repetitive or multiple copies of that within it. And it really does scale in that regard. So it allows you to easily match the performance of a TCAM and way outperform the densities and just number of rules that you can store within it. So it really does have that kind of benefit of, and it's lower power, obviously, since TCAMs could, warm a room most of the time when you're using them. So it's much lower power and equal to or better performance.
All right, thank you, Mark. We'll move on to another question here for you that says, how do MoSys Linespeed products compare to Broadcom, Marvell, and Inphi products?
Yeah, thanks, Chris. Several things I want to note. Number one is we support the basic industry standard features that other vendors support. Things like the standard 100 gigabit Ethernet gearbox, retimer capabilities, etc. But we also add to that a bunch of industry unique features, things like the embedded RSpec encoding and decoding, the redundant link mode for high availability systems, things like independent baud rates per lane in a retimer device. So we do cover the basics, if you will, but we also add a bunch of unique features. We're very aggressive on pricing. And one last important thing I want to note is that we offer our products through distribution with our Arrow partnership, and we also support our customers with direct access to application engineering and application support, which is oftentimes lacking with some of the larger vendors in the industry. So hope that answers the question.
All right, thank you, Scott. We'll move on to another question here that asks, how does the cost of a MoSys BLAZAR or QUAZAR solution compare to the price of QDRs or of the QDRs that they replace?
Yeah, this is Gus. I'll take that one. Yeah, just a simple example. If you were to take a half a gigabit of QDR memory versus a single chip MoSys half a gig, we would be significantly lower priced. And you can even get 8 times the capacity if you use a gigabit device in a single chip. So on a per bit basis, we're very, very, very more cost effective than QDR.
All right, thank you. And thank you, Gus. And our next question here asks, what is the performance speed differential of memory and RTL as it relates to system latency versus device latency?
Yeah, hi, I'm Mark. I'll take that one. I think that's a very important question that we wanted to point out, is that a lot of times when people look at a memory product like a QDR and they can see that the specified latency of the device is in a couple of nanoseconds, right, 2 or 3 nanosecond range. That does not relate to what the system latency is, right? So what we're calling system latency is when you're in like an FPGA, let's say we're interfacing with an FPGA, there's a controller behind the FPGA. You then have to go through the IOs of the FPGA, go to the memory, come back and go back into where the results go back to the request point, right? When you look at that, we're calling that the system latency. And the system latency is really very comparable. We're still slightly longer, I will say by a few nanoseconds, but it is absolutely much closer than you might think when you look at the overall latency number that addresses a request. So, you know, it really does, when you can increase both the overall density and then the sheer bandwidth and performance increase over a straight single QDR, then we look at that system latency as a very comparable thing, and an easy trade-off to get the extra benefit of density and speed.
All right, well, thank you, Mark. I'm just taking a quick look here. It looks like that's all the time that we have for questions for today. Once again, if we did not get to your individual questions, someone will be getting back to you after the program is over. I'd like to thank Gus, Mark, and Scott for a great presentation and Q&A session. And for more information related to today's webinar, please visit any of the resource links available in the green folder icon at the bottom of your screen. And just as a reminder to our audience, that now does include the slides are now available there in the green folder icon. And within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. Once again, we'd like to thank you for attending today's webinar, How to Increase Performance and Reduce Cost with Optimized System Memory in FPGA Designs, brought to you by Tech Online, MoSys, and Arrow. This webinar is copyright 2021 by AspenCore. The presentation materials are owned by or copyright by Tech Online, MoSys, and Arrow, and the individual speakers are solely responsible for their content and opinions. On behalf of our guests, MoSys and Arrow, I'm Chris Keach. Once again, we'd like to thank you for joining us, and we hope you have a great day.